Let's begin with a question that tickles the imagination. What if there were particles that always traveled faster than light? Not just capable of breaking the speed limit of the universe, but incapable of going slower than it. Welcome to the world of tachyons, hypothetical particles that have fascinated physicists, philosophers, and science fiction writers alike for over half a century. Tachyons were first introduced in the 1960s, not as a whimsical idea, but as a mathematical consequence of extending Einstein's equations. If particles with real mass must always travel at speeds less than the speed of light, and light-speed particles like photons have no rest mass, then what about imaginary mass? Literally, a value involving the square root of -1. Could such mass belong to a particle that can never slow down to light speed, let alone stop? The tachyon hypothesis raises wild possibilities. If they existed, tachyons could be used to transmit information faster than light. This could mean breaking the fundamental rule that cause must come before effect. Imagine you receive a message before it was even sent. Or worse, you die before you're born. The logical chaos this invites is not a trivial philosophical puzzle. It strikes at the heart of causality, the order of time itself. Now, to bring this from theory to the laboratory, we need to talk about how we've actually searched for tachyons, and how these searches have failed. One of the most dramatic moments came in 2011, when the OPERA experiment in Italy announced it had measured neutrinos arriving at their destination 60 nanoseconds faster than light should. That's 0.0006 seconds. It doesn't sound like much, but over a 730-kilometer underground journey from CERN in Switzerland to the Gran Sasso lab, this tiny early arrival caused a global media frenzy. If true, it would have overthrown over a century of physics. Neutrinos were already weird, nearly massless, ghost-like particles that barely interact with matter. Could they be tachyons? For 6 months, the world held its breath, but in the end, it turned out to be a loose fiber optic cable. The time signal had a lag. The neutrinos weren't faster than light. We were just measuring badly. This kind of experimental dead end is common in the search for tachyons. We've looked for signs of Cherenkov radiation in vacuum, an effect similar to a sonic boom, but for light. Just as a jet breaking the sound barrier creates a shock wave, a tachyon breaking the light speed barrier should leave a trail of optical evidence. But we've never seen such radiation in vacuum. Not in space, not in particle colliders, not in controlled laboratory tests. And what about in cosmic rays? These natural high-energy particles bombard Earth from space, sometimes reaching energies that dwarf what our most powerful colliders can produce. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah have tracked millions of cosmic ray events. If tachyons were real and common, some unusual signal should have appeared by now. A superluminal signature that just doesn't match any known particle model. But no such anomaly has ever been found. Still, the appeal of tachyons refuses to die. Let me offer an analogy to explain why. Imagine you're in a boat on a river. Most particles in physics flow with the current, always going downstream, with time as the direction of flow. Tachyons, if they exist, are like fish swimming faster than the current can carry them. So fast that, from your perspective on the boat, it seems they're going upstream. That's the feeling physicists get when considering tachyons. They would appear to go back in time, not just figuratively, but literally, arriving before they depart, violating the sacred chronology of events. You might ask, but couldn't we use this to send messages to the past? Theoretically, yes, but here's the catch. To send a tachyon message, you'd need a transmitter that somehow exists in a frame of reference where causality isn't preserved. And that doesn't just mean fast, it means breaking the structure of space-time itself, And we have no evidence that any material object, not even black holes or wormholes, can do that. In fact, Einstein's own theory provides a kind of safety mechanism here. The very structure of space-time appears to prohibit any message from traveling outside the light cone, a kind of boundary around every event in the universe that defines what can influence what. Everything inside this cone can affect and be affected by the event. Anything outside it, including hypothetical tachyons, belongs to a region forbidden to real causality. Yet, in quantum field theory, tachyons sometimes reappear, not as physical particles, but as indicators of instability. For instance, in the early stages of the Higgs mechanism, the field configuration appears to contain a tachyonic mass. But this doesn't mean a tachyon is flying around. Instead, it means the system wants to evolve to a more stable state, much like a pencil balanced on its point will fall. The tachyon is a hint, a ghost, a mathematical whisper saying, "This setup isn't stable. Expect a phase change." This ghostly presence shows up in condensed matter physics too. Certain quasi-particles, collective behaviors of many particles, can mimic tachyon-like behavior, but only in very limited systems and over short distances. None of them break the light speed limit. They only flirt with the analogy. So, where does this leave us? Tachyons are beautiful in theory, but uncooperative in practice. Like a mirage in the desert, they seduce with promises of time travel, instant communication, and new physics, but vanish under rigorous scrutiny. Yet their value isn't in their existence, it's in their challenge. Tachyons force us to ask, what would the universe look like if causality broke down? Could our deepest principles survive such a shock? And perhaps that's the point. Even in their absence, tachyons help us test the scaffolding of our understanding. They remind us that science isn't just about what is, but also about what cannot be. That negative result, no sign of tachyons, is itself a kind of knowledge, a boundary around our universe drawn with painstaking care. Think of this like mapping the oceans. The places we've already explored are marked with familiar names and coordinates. The places we've tried and failed to explore because the currents are too strong or the depths too great are still important. They tell us where we can't go, and that's just as meaningful. In the end, tachyons occupy a special role in modern physics, not as realities, but as signposts. They're like the dragons on old maps. Here be the unknown. And until we know more, that unknown is a place for imagination, for caution, and above all, for curiosity. Because even if tachyons don't exist, the questions they raise still ripple across the fabric of science, faster than light.